Homogeneity is a very simple, almost trivial concept, but it is of tremendous importance. Homogeneity states that each term on both sides of an equal sign and every term within an equation must have the same units. For instance, let us consider our expression for force. Force was equal to mass times acceleration. We had newtons on the left-hand side and newtons on the right-hand side. Thus, that equation obeys homogeneity. This is important because we can divide both sides by area, and then we'd be calculating pressure or stress. We can add a newton to one side or another, and it still obeys homogeneity. That is, if our equation obeys homogeneity, we can add like terms, such as meters to meters, seconds to seconds, newtons to newtons. But if your equation violates homogeneity, it means it's incorrect, because you can't add meters to meter squared, or seconds to second inverse, or newtons to pound force. That doesn't make any sense. On this topic, you should always write your units and carry them through every step. This is the best way to identify any mistakes that you have made in your calculation. Let us look at an application of homogeneity. And what's amazing about the concept of homogeneity is you don't necessarily have to understand the field or equation to understand what each term represents. Let us consider the Reynolds number, which is expressed as the density of a fluid, which has units of kilograms per meters cubed, times your velocity, which is expressed as meters per second, times your hydraulic diameter, which is expressed in meters, and this is divided by your dynamic viscosity, kilogram per meter second. What are the proper units for our Reynolds number? Well, let us write this out. Our Reynolds number is our density times our velocity times our hydraulic diameter, rho v d sub h, per our dynamic viscosity, mu. Our density has units of kilograms per meters cubed, our velocity has units of meters per second, our hydraulic diameter has units of meters, and our dynamic viscosity has units of kilograms per meter second. We see our kilograms cancel out, our seconds cancel out, and our meters cubed cancel out. Thus, our Reynolds number is dimensionless, which is correct. Let us also consider another situation. Our deformation equation, which we'll learn about in Chapter 6, says our total deformation, which is denoted by the Greek letter delta, that a body experiences is due to both an applied force and any thermal effects that may be occurring. We can express this as delta is equal to PL over EA, where P is your applied load with units of newtons, L is the length of the member with units of meters, E is your elastic modulus with units of Pascal, and A is your cross-sectional area. We can also add on alpha, which is your coefficient of thermal expansion, plus delta T, which is your change in temperature in Kelvin, times L, the length, with units of meters. Given this, what units must alpha have for our equation to obey homogeneity? For us to do this, we will construct our equation based upon our givens. Delta is equal to PL over EA. P was expressed in newtons, L was expressed in meters, E was expressed in pascals, and A was expressed in meters squared. This was plus alpha, our unknown, times delta T, which was expressed in Kelvin, times our length, which is expressed in meters. Now, in terms of our base units, recalling our pascals and newton per meter squared, we'd have newton times meters cubed per newton per meter squared, which represents our PL over EA term, plus alpha km. If we simplify this, our newtons cancel out, and our first term on the right-hand side of the equation, meters cubed per meter squared, gives us meters, and this is plus alpha times k per m. The second and third term of our equation, i.e. on the right-hand side of the equation, must have units of meters. That is, we have meters plus alpha k meter. Thus, alpha must have units of 1 per k, or k inverse, for k would cancel out, and we'd be adding meters to meters.